Hello everyone. In this video I am going to explain hyperconjugation. Hyperconjugation is one of the bond polarization effect. So electron displacement effect in covalent bond are four types: inductive effect, mesomeric effect, hyperconjugation and electromeric effect. In that inductive effect completed, mesomeric effect also completed. In the mesomeric effect I have explained what mesomeric effect, resonance effect and aromaticity also. So in this video, hyperconjugation. What is hyperconjugation? So it was explained by Nathan and Baker. Nathan-Baker effect. It is also said to be Nathan-Baker effect. So what is other name? It is also said to be no bond resonance. Hyperconjugation is also said to be no bond resonance. Important to remember. What is the definition of hyperconjugation? The complete transfer of sigma electron. Complete transfer. So in inductive effect, just shift of electron, just moving towards one atom. But here complete transfer of sigma electron, of which alpha carbon CH, sigma electrons of alpha carbon CH towards pi bond or towards positive charge or towards free radical is called as hyperconjugation effect. Hyperconjugation effect, shortly H effect. Inductive effect, I effect. Mesomeric effect, M effect. Hyperconjugation effect, H effect. Hyperconjugation is possible in three cases. Case 1, whenever alpha carbon CH sigma electron and positive charge in conjugation. Whenever alpha carbon CH sigma electron and pi bond are in conjugation. Third case, whenever alpha carbon CH sigma electron and free radical are in combination. In these three, so it is common. Alpha carbon CH sigma electron is must in all these three cases. Along with alpha carbon CH sigma electron, positive charge, otherwise pi bond, otherwise free radical may be in combination. Okay, take this one. In that first one is whenever alpha carbon CH sigma electron and positive charge in combination, I will see that. First, case 1, whenever alpha carbon CH case 1, is when alpha carbon CH sigma electrons and positive charge are in conjugation. Alpha carbon CH sigma electron and positive charge in combination. Example, right, like this. So here positive charge, single bond, sigma bond of CH, alpha carbon. So adjacent carbon to positive charge is alpha carbon CH sigma electron, alpha carbon sigma electron, alpha carbon, both are in combination. Then it give hyperconjugation. How? Hyperconjugation, if you see orbital structure, hybridization of this carbon is sp3 and s orbital is overlapped like this. S orbital of hydrogen atom, sp3 hybrid orbital of carbon overlapped. Here how many electron? 2 electron. Here this is sp3 carbon and hydrogen. Here is sp3 carbon and hydrogen here. Okay, here sp3 carbon of first carbon sp3 carbon of this one, and sp2 carbon, sp2 carbon of this carbon. Sp2 mean 3 sp2, 2 electrons here, a hydrogen overlapped here, a hydrogen overlapped here, hydrogen overlapped here. Next, this has this carbon, carbocation has unhybrid p orbital. Because of sp2 hybridization, sp2 hybridization mean 1s orbital, 2p orbital. Only involved in hybridization, this p orbital is this one, unhybrid p orbital. Only sp2 hybridization mean 1 p orbital is this one. Okay. Now this is vacant orbital, vacant unhybrid orbital present in carbon. Carbon has sextet configuration, only 6 electrons, this is vacant. Now shift of these electron towards that. Shift of these 2 electron towards that. Here formation of this orbital completely overlap with vacant orbital of this one, and pi bond formation, that leads to pi bond formation. Then what does it give? It gives for this one, so here hydrogen, both electrons lost here, 2 electrons lost here, carbon, hydrogen become positive. This carbon form a double bond with this carbon, positive carbon, this is the same. So this is hyperconjugation, conjugation said to be hyperconjugation. So or otherwise this one also, B hydrogen also may participate in hyperconjugation. B hydrogen also participate in hyperconjugation. So how it will be? Here this hydrogen, these 2 electrons shifted here, where it become double bond CH2. Second possibility. What is third possibility? This C carbon, here HB carbon hyperconjugation, here HA carbon hyperconjugation, here HC carbon hyperconjugation. So this bond same, this carbon hydrogen, this sigma bond shifted for hyperconjugation like this. Okay, that means 3 alpha hydrogens are there, 3 hyperconjugative structures. So 1, 2, 3. Here 1, 2, 3 are 1, 2 and 3 are hyperconjugative structures. Hyperconjugative structures. Hyperconjugative structures are canonical structures. Canonical structure. Hyperconjugative structures are canonical structures. So more the number of alpha hydrogen, more will be hyperconjugative structure, and more is the stability. More is the stability because positive charge shared by 3 hydrogen. So charge distribution is more. Charge distribution more means delocalization of charge is more means stability is more. Okay, so I will write that point. More the number of alpha hydrogen, more the number of alpha hydrogens. What are alpha hydrogen? Hydrogen atom attached to alpha carbon or alpha hydrogen. What is alpha carbon? The carbon which is adjacent to our interested carbon, our positive charge carbon or double bonded carbon or free radical carbon. So to the free radical, to the functional group, to anything, adjacent carbon is alpha carbon. More the number of alpha hydrogen, more will be resonating structures. More will be resonating structures or hyperconjugative structure, not resonating structure. More will be hyperconjugative structures. More will be hyperconjugative structures. More hyperconjugative structures mean It means more delocalization of positive charge, more delocalization of positive charge, more delocalization of any charge, and more is the stability. More is stability. More the delocalization of charge mean more is the stability. More the number of alpha hydrogen, more the number of alpha hydrogen, more the number of resonating hyperconjugative structure, more is the delocalization. Yeah, more is the positive charge, more is the delocalization of positive charge. Here 1, 2, this carbon, this hydrogen, 3, and this is 4. Delocalization is more. Delocalization of positive charge is more. Here positive charge is localized here. When it comes here, you say that is delocalization. If it comes here, that is delocalization. If it comes here, that is delocalization. More the delocalization of charge, more will be the stability. Remember that one. That's why more the number of alpha hydrogen, more will be hyperconjugation, more will be the stability. That is my point. Okay, right. Next, case 2. When case 2, when alpha carbon CH sigma electrons and pi bond are in conjugation. In previous case, alpha carbon CH sigma electron and positive charge in conjugation. Here alpha carbon CH sigma electron and pi bond are in conjugation. Then what happens? That will also lead hyperconjugation. Example, see here, this is what pi bond, sigma bond, pi sigma, this is alpha carbon sigma CH, this is also sigma, combination, conjugative combination, alpha carbon CH sigma, sigma pi, conjugation. This type of conjugation leads to, this is sp2 carbon. So here what happens, this pi electron move towards this carbon. Whenever that pi electron move towards this carbon, these electrons or these electron or these electron may shift here. Only electron, not a hydrogen atom, only electron. That leads to 3 hyperconjugative structures. So say this is HA, this is HB, this is HC. Due to HA, 1 minute, right here, hyperconjugation of this hydrogen, that leads H here, H. This hydrogen become positive because these electron shift, these 2 electron shift between these 2 carbon and this pi bond shift towards this carbon. Then that give a double bond here, this is H, and this carbon become minus. This hydrogen also same, B hydrogen, C hydrogen, B hydrogen, C hydrogen same, this A hydrogen become positive. Or otherwise B hydrogen, alpha carbon B hydrogen, hyperconjugation. So that hydrogen become positive, and this CH bond same, this CH bond same, this become double bond CH. This pi bond shift towards this one, this pi bond become sorry, this sigma bond form a new bond here, pi bond, and this pi bond shift towards this one. That due to complete shift of this pi bond towards this carbon, that is negative. Okay, this is positive, that is negative. Total charge neutral. This is neutral, this is also neutral. So all resonating total charge on all resonating structures must be same. In the similar way, total charge on all hyperconjugative structures is also same. 0, 0, total charge 0, total charge 0, here total charge 0. Due to hyperconjugation of third one. So first bond is same, second bond is same, A, B same, but this HC carbon become positive, here double bond, and this carbon become negative. There are 3 alpha hydrogen, 3 hyperconjugative structures. Okay, in this way, hyperconjugation is possible whenever alpha carbon CH sigma electron and pi bond are in conjugation. Now, third case number 3. Case number 3, that is when when alpha carbon CH sigma electron and free radical are in combination. Free radical are in conjugation. Case 3. Free radical are in conjugation. Example: this is free radical. Then it gives what? Just like a positive charge, here free radical. Alpha carbon sigma electron, the sigma electron of alpha carbon, the sigma electron alpha carbon, sigma electron. Any one of these 3 sigma and free radical are in conjugation. Then homolytic bond fission takes place in this bond. Case 1, or otherwise, how many hyperconjugations possible? 3 hyperconjugations possible. For HA hydrogen, HB hydrogen, HC hydrogen. Second one for HB hydrogen. Third one for HC, third hydrogen. So here this bond is same, there is no change, but here this hydrogen become free radical. This hydrogen and carbon become free radical. Okay, one bond take away by HA, one bond taken by this carbon. This carbon free radical form a new bond, like this. HA hydrogen become free radical. Here HB hydrogen become free radical, and this is same and this is same. Here double bond between this carbon free radical and new carbon free radical due to homolytic bond cleavage of this bond. Next, here due to homolytic bond cleavage, this carbon become free radical, this carbon become free radical, this hydrogen become free radical, this carbon free radical forming a new bond with another carbon free radical, and this become free radical here, like this. 3 alpha hydrogens, 3 hyperconjugative structures. That means number of hyperconjugative structure numerically equals to number of alpha hydrogen. More the number of alpha hydrogen, more will be delocalization of positive charge, delocalization of free radical, delocalization of pi bond, more will be stability. That is my concept. Okay. Next, if in case if alpha carbon CH sigma electron and a negative charge in combination, conjugative combination, then hyperconjugation possible or not? Whenever alpha carbon CH sigma electron and a negative charge in, if alpha carbon CH sigma electrons and negative charge are in conjugation, then hyperconjugation is not possible. Hyperconjugation is not possible. See, this is alpha carbon with 3 alpha carbon CH sigma electron and taking this negative charge. Alpha carbon CH sigma electron and a negative charge are in conjugation. That means alternatively. In between those two, one sigma electron. Here hyperconjugation is not possible because shift of this bond not possible. Shift of that bond is not possible because this is negative charge. So electron always move away from the negative charge, not towards negative charge, away from the negative charge. That's why hyperconjugation is not possible. Hope you understood. This is about hyperconjugation. Now I will give some applications of hyperconjugation. Applications of hyperconjugation. Hyperconjugation explains stability of carbon free radical and stability of carbocation. Stability of what? See, this hyperconjugation explains stability of carbocation, stability of free radical also. So stability of carbocation. So here carbon carrying positive charge, in this one carbon carrying positive charge, methyl carbocation also. So this is tertiary carbon, tertiary carbocation, and this is secondary carbocation, this is primary carbocation, and this is methyl carbocation. Methyl carbocation is super primary carbocation. Super primary carbocation. Methyl carbocation is super primary carbocation. See here, how many alpha hydrogen? What is alpha carbon first? The carbon which is adjacent to positive charge. How many alpha hydrogen? 9 alpha hydrogen. 9 hyperconjugations more stable. Here to this is alpha, this is alpha. Only 6 alpha hydrogen, somewhat less stable. Here to this is alpha carbon. How many alpha hydrogen? Only 3 alpha hydrogen, less stable. Here so there is no alpha carbon first of all. To this adjacent carbon is alpha, but there is no adjacent carbon, there is no alpha carbon, no alpha hydrogen. No alpha hydrogen. So more the number of alpha hydrogen, more will be resonating structure, more will be delocalization of positive charge, more will be stability. That's why definitely stability order is like this. Thus hyperconjugation explains stability of carbocation. The similar way stability of free radical. Here how many hyperconjugation? This is alpha carbon, this is alpha carbon, this is alpha carbon. How many alpha hydrogens here? How many alpha hydrogen? 1 here 2 alpha hydrogen, 2 alpha hydrogen, 3 alpha hydrogen, 2 plus 2 plus 3, that is 7 alpha hydrogen, 7 alpha hydrogen. For this is alpha, this is alpha, 2 plus 2, only 4 alpha hydrogen. For this one, only this is alpha. Already 3 bonds are there, mean only 1 alpha hydrogen, only 1 alpha hydrogen. Definitely stability order is, so due to presence of more number of alpha hydrogen, this free radical is more stable. That is what tertiary free radical, tertiary carbon free radical more stable than secondary carbon free radical, more stable than primary carbon free radical. Okay, next application of hyperconjugation is, hyperconjugation explains stability of alkenes. Hyperconjugation explains stability of alkene. Take this one. See this one. Hyperconjugation explains stability of alkenes. So between propene, this is what propene, and ethene or ethylene, which is more stable? Definitely propene is more stable than ethene. Why? Because in propene, how many alpha hydrogens? Sir, what is alpha hydrogen? To the carbon-carbon double bond adjacent is alpha hydrogen. How many alpha hydrogens for propene? 3 alpha hydrogen. 3 alpha hydrogen mean 3 hyperconjugative structure. To the double bond there is no adjacent. This is double bonded carbon, this is not adjacent. This is double bonded carbon, this is adjacent one, alpha. So there is no alpha hydrogen, no alpha hydrogen. That's why no alpha hydrogen mean no hyperconjugation. 3 alpha hydrogen mean 3 hyperconjugative structure. That's why that is more stable. Okay. Next, stability order of, I will give stability order of some alkene. Stability order of some alkenes. That first 2,3 dimethyl butene is more stable. 2,3 dimethyl butene, but-2-ene is more stable. When compared to that one, 2-methyl but-2-ene is more stable. 2-methyl but-2-ene is more stable. When compared to that one, 2-methyl propene, otherwise isobutene is more stable. Compared to trans-but-2-ene. Trans-but-2-ene more stable when compared to cis-but-2-ene more stable when compared to propene. CH3 CH double bond CH2 more stable when compared to CH2 double bond CH2. Reason, stability order. Okay, so reason, here how many alpha hydrogen? Alpha carbon, alpha carbon, alpha carbon, alpha carbon. To the double bonded carbon, next carbon is alpha carbon, 3, 3, 3, 3, 12 alpha hydrogens. 12 alpha hydrogens. Here alpha carbon, alpha carbon, alpha carbon, only 3 alpha carbon. This is not alpha hydrogen. Hydrogen atom attached to alpha carbon is alpha hydrogen. This is attached to double bonded carbon, not alpha carbon. So how many? Total 9 alpha hydrogen. 9 alpha hydrogen. Here only 6 alpha hydrogen. Okay. Right here 6 alpha hydrogen. Here 6 alpha hydrogen. Here this is only alpha, How many alpha? 3 alpha hydrogen. Here no alpha hydrogen. No alpha hydrogen. As the number of alpha hydrogens decreases, stability decreases. If you compare these three, this is what isobutene, trans-2-butene and cis-2-butene. If you compare these three, explanation, I will give explanation. First, all these three have same number of alpha hydrogen, though this is more stable than this one, this is more stable than this one. Why? So if you see this one, yes, this one. Second is what? Trans. Trans is always more stable than cis. I will give that statement. Trans is always more stable than cis. Here cis. Next I will write cis. CH double bond CH. CH double bond CH. Okay. So this is trans-butene. And this is cis-butene. Okay, so always trans more stable than cis. Transalkenes are more stable than cis. Remember that point. Transalkenes are more stable than cis. Transalkenes are more stable than cis due to steric hindrance. Steric hindrance means bulk group effect. So here similar groups present on same side. Repulsion. Here what reason is? Repulsion. Similar groups present on same side, repulsion. Here similar groups present opposite side. So no repulsion. Here no repulsion. So that's why trans is more stable than cis. Why is this 2-methyl propene more stable than trans-butene? So in this one hyperconjugation, I will write hyperconjugation in first one. I will write some, see here. And I will also write hyperconjugation in trans-butene. Hyperconjugation possible, but their hyperconjugative structure stability decide whether which alkene is more stable. What is its hyperconjugative structure? How many alpha hydrogen? Here alpha hydrogen, here alpha hydrogen, for this alpha hydrogen and alpha hydrogen. Okay, so if this alpha hydrogen involved in hyperconjugation, then this become what? CH2 double bond C, and this one here one hydrogen become here positive, one hydrogen become positive, like this. Alpha carbon or not? Yes, definitely alpha carbon, and the shift of this bond takes place like this, alpha and this carbon like this, that carbon taking away electron. Now this become double bond here, this hydrogen become positive, here CH2 double bond C, here this is same CH3, and this double bond becomes single bond, this is minus, and CH2 minus. Okay, if this one involved in hyperconjugation, hydrogen here, hydrogen here, hydrogen here, this is alpha. Okay, if that one involved in, if this one involved alpha carbon hydrogen involved in hyperconjugation like this, then what is the resultant of that? That becomes CH2 and one hydrogen here, that is positive, double bond, this is H here, and this one become minus CH3. Now which one is more stable? Which one is more stable? Carbon ion stability explained. Carbon ion stability. So this is to the carbon ion, this is CH2, CH double bond CH2. Okay. So to this negative charge, this is plus I effect. Plus I effect unfavorable for the stability. Sorry, minus plus I effect unfavorable for stability of carbon ion. Of course, plus I effect stability for stability of carbocation, but this is carbon ion, unstable. But here no such groups. Remaining is same. See here carbon ion single bond double bond, carbon ion single bond double bond. So this is same on both sides. This is same, and if you see here, this carbon ion not directly attached to minus I group, that is 0.1, and this is what? This is minus I group, and this is also minus I group. So that's why this is more stable. Above one is more stable. Okay, this is less stable. Since the hyperconjugative structure of trans-butadiene, due to less stability of hyperconjugative structure of trans-butadiene, it is less stable when compared to 2-methyl-propene because its hyperconjugative structure is stable. Here, why is it unstable? Due to plus I effect. So plus I effect decrease stability of carbon ion. That's why above order. Okay. Hope you understood well. Next, heat of hydrogenation, that is related to this topic. I will give that one. Take this one. See this. This is heat of hydrogenation. Heat of hydrogenation is what? The heat, amount of heat evolved when any unsaturated hydrocarbon, alkene, alkyne, any hydrocarbon, ethene, propene, propane, like that. Any unsaturated hydrocarbon is hydrogenated. Addition of hydrogens is said to be hydrogenation. Addition of hydrogen is called as hydrogenation. So when any unsaturated hydrocarbon undergo hydrogenation, it releases some amount of heat, that is said to be heat of hydrogenation. The amount of heat evolved when any unsaturated hydrocarbon is hydrogenated is said to be heat of hydrogenation. Less stable alkene. Less stable alkenes mean more reactive. More reactive alkenes releases more amount of heat upon hydrogenation. More reactive ones always react more amount of more reactive one always releases more amount of energy. That's why less stable alkene means they are more reactive. More reactive alkenes releases more heat of hydrogenation. That's why we can relate them like this. Heat of hydrogenation is inversely proportional to stability. More the stability of alkene, less will be heat of hydrogenation. Less is the stability of alkene, more will be heat of hydrogenation. And stability of alkene directly proportional to number of alpha hydrogen. That's why we can relate. Heat of hydrogenation inversely proportional to number of alpha hydrogen. See this question, which one of the following has minimum heat of hydrogenation? Minimum heat of hydrogenation mean maximum number of alpha hydrogen. Minimum heat of hydrogenation mean more stable alkene. maximum number of alpha hydrogen. So in ethene, minimum heat of hydrogenation means maximum number of alpha hydrogen. Which one is our answer? So in ethene, no alpha hydrogen. In ethene, no alpha hydrogen. So this is not answer. In propene, only 3 alpha hydrogen. In cis-butene, between cis and trans is more stable. So in butene, here how many? Butene, 6 alpha hydrogen. Here 6 alpha hydrogen. Minimum heat of hydrogenation means maximum stability, that is definitely D. Trans-butadiene is more stable compared to cis-butadiene. Okay, so hope you understood well. This is about of hyperconjugation topic and heat of hydrogenation.